Good evening, everyone. Welcome to BYJU'S exam prep. So just let me know whether the video and audio is absolutely fine. So just let me know whether the video. Okay, so I think that the voice is clear. Yes, good evening, Nand Gopan. So guys, today we are having a T20 series where we are going to discuss the 20 concepts through the questions, and we will also discuss as I have told you in the revision session, that we are going to have one session about the revision of the digital communication. So we will first revise the digital communication and then we will proceed for the question. So we have around 20 concepts of the digital communication, because these are very important topic for all of you, and you were looking for that. And in the previous lecture which we have taken, the marathon session, where we discussed only the analog communication and the random variable and random process part. So that is why it is going to be important for all of you for the revision of the digital communication. Hello Rajesh, hello Sharmana. So yes, Ramna. So first of all, tell me, how is your communication now? How much you have prepared, and are you confident in the communication subject? And what are the problems which you are facing in the communication? And before starting this session, I would like to introduce myself. This is Saket Verma, having more than 13 years of experience in the field of GATE and ESC. I have done MTech from IIT Guwahati and cracked a different PSU exam as well. So my area of expertise are electromagnetic theory, communication system, advanced communication system, and signal system. So these are my area of expertise. You can join the Telegram group for the class notification. What are the classes we are conducting? That classes you can get the link of those sessions in the Telegram group. And this is, guys, a scholarship test for those students who are going to prepare for the GATE 2025. They can avail the scholarship by attending this scholarship test, and they can get the scholarship up to the 90%, and that is going to be held on the 28th of January. So, and there is a workshop also on 24th, that is today at 7:30 p.m. just right after this session. The link is given in the description. You can check this. So guys, in the digital communication, the important parameter things. No, actually, Kiran, there is no such playlist because we haven't teach any specific series where you can find the complete lecture of the communication. Basically, we have only random sessions, so you can get some question series, you can get somewhere revision series, but you will not get the exactly your lectures of the communication by me. So digital communication we are going to discuss first, and then after that we will discuss the noise in digital communication and the information theory. So guys, in the digital communication we have two parts, that is the baseband transmission and the bandpass transmission. In the baseband transmission, we say that, okay, when we talk about the baseband transmission, so we have that this is the in the baseband transmission, we transmit the signal without modulation. So baseband means without modulation. Okay, so whenever you perform the baseband modulation, that means you are not modulating the carrier. So without modulating, how do you transmit the signal? So by means of some technique like a pulse code modulation, DPCM, delta modulation. The word is associated there as a modulation, but basically we don't modulate it. We transmit our analog signal, convert into the digital signal, and those digital signals are transmitted through the ones and zeros. In the form of zeros and ones, we transmit through the channel. So that is your baseband transmission. And bandpass transmission means here we transmit the signal with modulation. So the signals are transmitted, the information which we transmit, the data which we transmit is done by the modulating the carrier. So basically here we modulate the carrier according to our information signal. Okay, that information signal are in the form of zeros and ones, and these zeros and ones we modulate the carrier and then we transmit it. If we change the amplitude of the carrier, then we call it as the amplitude shift keying. If we change the phase, then it is called phase shift keying, and if it is frequency, then we call it as a frequency shift key. Okay. So in the baseband, transmission is the transmission of a message data stream without modulating it with a high frequency carrier, and a baseband transmission is the transmission of the encoded signal using its own baseband frequency. It is used for the short distance communication. Now, what are the block diagrams of the digital communication? In the every block diagram, we have a communication system. We have a transmitter, channel, and the receiver. Here also we have a transmitter, channel, and receiver. This is the block diagram of pulse code modulation. So basically, whatever we continuous time signal we have, here we will have our analog signal, that is continuous time signal. Okay, continuous time, continuous amplitude signal. So continuous time, continuous amplitude signal is transmitted through this sampler. The sampler will convert this continuous time into the discrete time signal. Only the time is discretized with the help of the quantization, sampling. And after the quantization, we have a discrete amplitude signal as well. So once we get the discrete time and the discrete amplitude signal, these signals are assigned a code with the help of this encoder. So according to this encoder, we convert the signals in the form of zeros and ones. But these zeros and ones cannot be transmitted through the channel. So we perform the line coding. What is the purpose of the line coding? Line coding converts the digital data, into the electrical signal. It converts the digital data into the electrical signal. So in this way, we get the coded pulse. That code is converted in the form of a pulse. That's why the name is given as pulse code modulation. Then this, when you transmit it to the channel, this will be distorted. The pulse code modulated signal will be distorted, and you pass it through the regenerative repeater. And this regenerative repeater will generate the fresh pulse code modulated signal. And after every distance of around 50 km or 20 km, we can keep the regenerative repeater because it is expected to have a noise distortion in the PCM signal around 20-25 km. And after that we get the fresh PCM signal, and in the last receiver we have, and this receiver will again regenerate the PCM signal, and then we will decode it, that from the pulse that we have transmitted in the transmitter, we will decode it and we will convert it into the form of zeros and ones, and then we pass it to the reconstruction filter to get our desired signal. So in this way, this particular PCM technique works. So when we perform the sampling, we convert the continuous time into discrete time. So how do we perform the sampling? So whenever we perform the sampling of any signal, continuous time signal, you have to satisfy the sampling theorem. Sampling theorem says that if you have a signal which is band limited to FM. So suppose you have a signal like this, which is having the highest frequency FM. This is having the highest frequency FM, or you can call it as a bandwidth FM. Okay, so you can call it as a bandwidth FM. You can call it as a bandwidth FM. You can call it as the highest frequency FM. You can also call it as a maximum frequency FM. So this, which is not having the frequency higher than FM, can be completely recovered if you sample this type of signal with the sampling rate of fs greater than equal to 2 FM, or the sampling interval of less than equal to 1/2 FM. So if you sample the signal using this condition, then we can expect, the signal can be completely recovered from its sample. Okay, so how do we sample? So to perform the sampling, the message signal is multiplied with the sampling function s of t. This sampling function is nothing but the train of impulse. Okay, so if we perform the sampling with the help of train of impulse, what we call it as, which type of sampling you will say it? Can you comment in the comment section? If you are sampling the signal by multiplying with the train of impulse, then which kind of sampling is this? Which kind of sampling is this? Yes. So this type of sampling is called as ideal sampling or instantaneous sampling. No, not flat top. It can be called as ideal or instantaneous sampling. So if in the question it is written that the ideal sampling or the instantaneous sampling is performed, that means you have to already assume that the signal by which you have multiplied your signal for sampling is nothing but a train of impulse. Okay, so in this way we perform the sampling and we multiply our message signal with this train of impulse and we get our sampled signal. This is nothing but a sampled signal. Okay, so this is at time t equal to 0. When you multiply with the impulse, you will get the impulse itself, but the magnitude of the impulse will be the value of the message signal at time t equal to 0. Similarly, you will get the at time t equal to ts. Similarly, you will get at time t equal to plus minus 2 ts and so on. After that, we will draw the spectrum of this. So to calculate the spectrum, we know that there is a whenever you perform the sampling, okay, you will get the sampling signal and the Fourier transform of this sampling signal is 1 upon fs summation n equal to minus infinite to infinite m of f minus n fs. Okay, this is how we perform the sampling. This is 1 upon ts actually. 1 upon ts and then it is fs. So when we perform the sampling, we get this signal. Okay, when we perform the sampling, we get these signals. Now, when you put n equal to 0 here in this equation, you will get the sample signal spectrum as fs into m of f. Okay, and n equal to 1. That means ms of f equal to fs into m of f minus fs. That means it is shifted. So you are going to get the original spectrum because this is your original spectrum message signal and this is the shifted form. So it is your original spectrum and it is replica of your original spectrum. Or you can say it as a shifted form of original. Okay, shifted form of original spectrum. मिनिमम बैंडविड्थ डिफॉल्ट क्या लेना है RB/2 लेना है ओके RB/2 लेना है ऑलवेज मिनिमम बैंडविड्थ बाय डिफॉल्ट ठीक है सागर सो मिनिमम बैंडविड्थ आपको RB/2 लेना है बाय डिफॉल्ट right? So we will get the original spectrum and the shifted form. So when you put here this is the spectrum we are having which is band limited to FM, highest frequency is FM. Now if you take case number 1, PSK ASK का बैंडविड्थ सेम होता है और वहां पे बैंडविड्थ जो है वो 2 RB होता है. ठीक है सागर bandwidth of PSK and ASK is 2 RB. That is different from the RB/2. RB/2 is for the PCM signal and the PSK and FSK, ASKs, PSK and ASK are digital modulated signal and these were having the bandwidth 2 RB. So when we perform the sampling for greater than 2 FM and 2 FM critical sampling and FS is less than 2 FM which is called undersampling. So these 3 type of sampling we need to perform. So when we perform the oversampling, so FS is greater than 2 FM. So let us say we have a 5 kilohertz message signal. So its highest frequency is 5 and minimum frequency is -5. So when we sample it using the sampling frequency 15 kilohertz, which satisfy this condition, fs is greater than 2 fm, then this, according to this expression, we have already seen that when we put n equal to 0, we will get our original spectrum. So when we put n equal to 0 here, we will get our original spectrum. When we put n equal to 1, it is shifted form of original spectrum or its replica. And when we put n equal to -1, we will get the replica in the negative side. Okay, so here we can use the low pass filter to recover our message signal. So here we can use the practical low pass filter, suppose of this kind. This is a practical low pass filter which we can use to recover our message signal. So we have a message signal only for n equal to 0. Okay, this is for n equal to 0. You will get the original spectrum, which is a triangular signal, which is same as this. Here you can see this is your original spectrum m of f. So when you put n equal to 0, the practical low pass filter you will get, and finally you will have the message signal back. This is the case when the fs is greater than 2 fm. Okay, when the fs is greater than 2 fm, that is the case. And in general, if you want to write, then for n equal to 0, you will get the original spectrum. For n equal to 1, for n equal to -1, you will get these spectrums. Okay, and now the difference, the gap the gap which is present between the original spectrum and its replica, which actually provides you the to use the practical low pass filter. That is because of that only you are able to use the practical low pass filter, is called the guard band, and the guard band is the fs minus 2 fm. The guard band is the difference between fs minus 2 fm. So that is your guard band. Now, what are the frequency components that are present if you sample any single tone signal? Then it is FM, FS plus minus FM, 2FS plus minus FM, 3FS plus minus FM. And in case of oversampling, it is possible to recover the original spectrum from the sample signal using the practical low pass filter. Because it is a oversampled signal, we can use the practical low pass filter. Now, when we take the fs equal to 2 fm, so when we take fs greater than 2 fm, there is a gap between the original spectrum and its replica, which is allowing us to use the practical low pass filter. But if you are taking fs is exactly equal to 2 fm, then the original spectrum and its replica are just interleave here, means where the original spectrum is ending, the replica will be starting. So here so here you can see that we cannot use the practical low pass filter to recover our information. We have to use the ideal filter, because if we use the practical filter, it will use this, it will allow this n equal to 1 also. It will pass this n equal to -1 and 1 also if we use the practical filter. So we have to use the ideal low pass filter in this case. Now, sampling theorem case number 3, fs is less than 2 fm. So when you are continuously decreasing the value of the sampling frequency, then its original spectrum and replica are closing to each other, and then they are overlapped. And once they are overlapped, okay, once they are overlapped, what will happen? If they will become overlapped, okay, here when they are overlapped, what is happening? Then there is a distortion for the highest frequency component of message signal, which is known as the aliasing effect. Aliasing effect, or you can say the fold over error or spectral folding. So that is the third part of this. And what are the important points? So if there is a multi-tone signal, then you can calculate the sampling frequency by 2 times of f max, 2 times of maximum value of f1, f2, f3 and so on up to fn. If they are multiplied in the frequency domain, if they are multiplied in the time domain, then the sampling frequency is 2 times of sum of all the individual maximum frequency. And if they are convolved, then the sampling frequency will be minimum of all the maximum frequency, f1, f2, f3 and so on. हाँ, इंफॉर्मेशन भी कवर होगा आज, इंफॉर्मेशन थ्योरी को भी हम लोग कवर करेंगे. तो ओवरऑल 1.5 आवर का सेशन है, अराउंड 7:30 तक चलेगा, है ना. 7:30 से 8 o'clock तक जा सकता है. और वी विल कवर द कंप्लीट डिजिटल कम्युनिकेशन, जहाँ पे हम इंफॉर्मेशन थ्योरी को भी कवर करेंगे. सो यू कैन स्टे विथ मी इफ यू वांट टू रिवाइज इट कंप्लीट डिजिटल कम्युनिकेशन. Okay, now the Nyquist rate calculation. So we know that this is Fs greater than 2 FM. So for faithful recovery, we need a sampling frequency greater than 2 FM. So if your message signal is empty, then it is having the frequency FM, then the Nyquist rate will be 2 FM. So M folding, time folding. If we perform the folding operation, time folding, then there is no change in the sampling frequency. If you shift the message signal in the time domain, then also there is no change in the sampling frequency. If you suppose scale it by A, then the sampling frequency will be 2 times of FM into A. And if you are again shifting and scaling both you are performing, then you will be having 2 FM into A. So this is 2 FM into A, and dmt by dt, this is 2 FM, which is the sampling frequency, and when you integrate also this is 2 FM. So there is no change in the sampling frequency calculation. If you shift it, if you fold it, if you integrate it, if you differentiate it, there will be only change in the sampling frequency by the factor A if you are scaling by the factor A. Like this is the question. So what will be the sampling frequency for this question? Can you comment in the comment section? Mm. 600, 1200. Okay, so here you can see that because as I told you that they are multiplied, so here we will get the sampling. Here this is the, suppose say frequency is 250 hertz, and here the frequency is 350 hertz. So my sampling frequency would be, this is the multiplication. So this is 2 times of f1 plus f2. So it is 2 into 250 plus 350, and hence we are getting 1200 hertz. So 1200 hertz will be the right answer. Okay. So how I had calculated, have you understood? So you have to calculate the maximum frequency of each component. Then you have to find whether which sign is this, whether it is a convolution, multiplication or addition. If it is a multiplication, then you have to add those individual maximum frequency and then double it. Yes. Now can you answer this question? Yes. So here you can see that the message signal which we want to sample is having the frequency 7 kilohertz. So, and we are passing it through the filter which is having the cutoff frequency of 12 kilohertz, and the sampling frequency is 9 kilohertz. So we know that whenever we sample, what are the frequency component present in the output, that is 7 kilohertz, and fs plus minus fm, that is 7, sampling frequency is 9 plus minus 7, so it is 16 and 2, and 2fs plus minus fm is 18 plus minus 7 is 25 and 11. So because the filter is having the cutoff frequency 12, so it will only pass the frequency which are less than 12. So the less than 12 we have 7, 2 and 11, option number B. Three components will be there which is having the frequency 2, 7 and 11. 11 will also come. 11 will also come because it is 2fs plus minus fm. We can continue calculate, but because the filter is having the cutoff frequency 12, it is sufficient to calculate up to 2fs plus minus fm. Okay, Vikram? Now, can you answer this question? What is the answer? Someone saying C. Yes. So the you can see that this is the signal which we are passing. We are passing it through the filter, and this is having the time period of 100 microsecond, means the sampling interval. So we know that the sampling frequency we can calculate, this is 1 upon Ts, and it is 1 upon 100 microsecond, and it is 10 raised to power 4, we can say. Okay, that means 10 kilohertz. So 10 kilohertz is the sampling frequency, and you can see that here we are actually performing the sampling like this. So we are performing the sampling of a signal which is having the 5 into 10 to the power 6 minus 6 and xt. This is our signal which is sampled using the instantaneous sampling, which is t minus nts. Here you can see that this is our sampling function. So the sampling function is train of impulse. Okay, sampling function is train of impulse. So we know that it is the ideal sampling. Whenever we perform the ideal sampling, we get the spectrum of the ideal sampling as fs multiplied with x of f minus nfs summation over n equal to minus infinite to infinite. Along with that, we have a 5 into 10 to the power minus 6 also. So 5 into 10 to the power minus 6 also will come. So now because it is passed through the filter is having the frequency 5 kilohertz. So when we put the value of sampling frequency, it will be the shifted to, okay, when we suppose substitute the values 5 into 10 to the power minus 6, what is the sampling frequency? Sampling frequency we calculated 10 to the power 4, and then summation n equal to minus infinite to infinite x of f minus nfs. So when you solve it, you will get 5 into 10 to the power minus 2 summation n equal to minus infinity to infinity x of f minus nfs. So this is our output, and this output is passed through. It is passed through the low pass filter. Okay, that is passed through low pass filter. So what is the low pass filter? Low pass filter is having the cutoff frequency of 5 kilohertz. Cutoff frequency of 5 kilohertz. So less than 5 kilohertz will only pass. So less than 5 kilohertz will pass. So if you put n equal to 0, you will get 5 into 10 to the power minus 2 x of f. And when you put n equal to 1, you will get 5 into 10 to the power minus 2 x of f minus fs. Fs is 5. Sampling was 10. Sorry, 10. So it will shift to 10. So which signal frequency will pass? 5 into 10 to the power minus 2 x of f minus, this is x now, x of f minus 20. So our original spectrum is ranging from minus 4 to 4. So it is having the range minus 4 to 4. It will be shifted to 6 to, when you will shift this signal, this is our x of f. When you shift x of f minus f 10, x of f minus 10 means it will be shifted to 10. So it is 14 and it is 6. So this will be 6 to 14. Okay, now it will be 16 to 24. So, and it is ranging from 0 to 4. So which signal will pass through the filter? Only this signal will pass through the filter. This signal will pass through the filter, and this signal will be rejected because this signal is having the range 4 kilohertz. So we have got output as 5 into 10 to the power minus 2 x of f, and taking inverse Fourier transform, we will get 5 into 10 to the power minus 2 x of t, and 5 into 10 to the power minus 2 x of t is how much? X of t is 10 cos 8 pi. So 10 cos 8 pi into 10 to the power 3 t. So 10 to the power 2 into 10 is 10 to the power minus 1. So we will get 5 into 10 to the power minus 1 cos of 8 pi into 10 to the power 3t. So that will be our answer. That means we have a option C. Option C will be the right answer. Option C, yes. Option C will be the right answer. Okay, now can you solve this question? What is the answer? Hello, Ashish. Ashwini is saying C. How you are saying C? There is no option, no? Okay, for the previous question you are saying. What is the answer of this question? Yes, Ashish, I'm good. So, how are you and how's your preparation? Can anyone answer this question? Can anyone answer this question? 4 kilohertz. One answer I have got is 4 kilohertz. Anyone else? Yes, Ashwini. Here the here the YT is XT multiplied with cos 1000 pi t, and it is convolved with sine 1500 pi t divided by pi t. So I told you that when there are two signals which are convolved and you want to calculate the sampling frequency, then you have to calculate the frequency of individual term. So what is the frequency of these terms? The frequency of these terms, these two terms are multiplied. Okay, these two terms are multiplied. So that means whenever you multiply the two frequencies, you will get the addition of the frequency and the subtraction of the frequency. The frequency is 500 and here also the frequency is 500. So you will get the 1000 and you will get the 500 plus 500, a plus b and a minus b. So it will be 0. Okay, so the highest frequency will be 1000 and lowest frequency will be 0. So obviously we will choose the highest frequency. So the highest frequency will be 1000. Okay, and what is the frequency of this? This frequency of this is 750 hertz. So we have the two frequencies 750 and 1000. Now because the two signals are convolved in the time domain, the sampling frequency is calculated as 2 times of minimum of the sampling frequency, minimum of 1000 and 500. So what is the minimum value? 750. 1000 and 750. So what is the minimum value in 1000 and 750? This is 750. So 2 into 750 is 1500 hertz. So answer is 1500 hertz. Answer is 1500. Yes, 1500 samples per second. Okay, Ashish? Yes. Got it? These two signals are multiplied. So when the two frequencies are multiplied, simple cos A, cos B formula you can apply. This is cos A, this is another input cos B. So we will get cos A plus B plus cos A minus B. That means this xt is having the frequency 500, this cos is having the frequency 500. So 500 plus 500 is 1000, 500 minus 500 is 0. So out of these two, we will choose the maximum frequency. Similarly, we will calculate the maximum frequency of the sine term, which is also 750. So, and when there is a convolution sign in between the two signals which are going to be sampled, we take the minimum sampling frequency. So, in the 1000 and the 750, the 750 is minimum, and then we choose the twice of minimum frequency. Okay, let's. Yeah, can you solve this problem? Solve it. Okay, so you guys are getting option C. So most of you are getting option number C. Yes. Option C is the right answer. So see here we have a cos 10 pi t plus pi by 4 which is ideally sampled. So because when we are sampling it ideally, that means what happening? So because we are getting the ideal sampling, so it is going to be shifted form. है So we have a cos signal pi by 4. The phase we can ignore because we are drawing the magnitude spectrum. So when we draw the magnitude spectrum, we will get this, and the amplitude is 1, so we will have 1 upon 2. Okay, and this is 5 and minus 5. Okay, this is our signal which is ideally sampled. So let us say this signal is m of f, which is we are sampling, and because we are drawing the magnitude spectrum, we can ignore the phase. We will add that phase later on. Okay, this is the magnitude spectrum. So whenever you draw the magnitude spectrum, you can ignore the phase. The amplitude gets half. That is important because we have to write the expression. Now we are going to sample it by 15. So when we sample it by 15, that is shifted to the sampling frequency 15. First of all, we will get our original signal as it is for n equal to 0. Then it will be shifted to 15. So we will get shifted to the 15. Then we will be shifting the 30. So we will be getting here like this. Similarly, we will be getting this and this and this. Okay, so we have 0, this is 5, this is minus 5, this is 15, we have shifted to the 15, so this is 20 and this is 10. We have shifted to the 30, so this is 35 and 25. Okay, subtracted by 25. Similarly, we will get minus 15 minus 30, it is minus 20 minus 10 and minus 35 minus 25. And because we are sampling it, so this is the spectrum of the sample signal. So when we draw the sample signal, we have a 15. That means the sampling frequency. The sampling frequency is 15. Na? So we know that we should get this signal m of f minus nfs. So it is 15 also. So the amplitude is 15. Okay, so this we will get for n equal to 0. This we will get for n equal to 1. This we will get for n equal to 2. This we will get for n equal to minus 1. This we will get for n equal to minus 2 and so on. Okay, now this signal is passed to the filter. Which kind of filter we are passing it? We are passing it through the rectangular signal which is having the width. Okay, this is think it is, so the width is 0.5 and it is shifted to the 20. Okay, so the filter which we are passing is centered at 20, and because when you are drawing the spectrum, it will be sine, so it is 1 upon 2j, and the here it is minus 1 upon 2j. It will be shifted to 20, so it is 20.5 and it is 19.5. It is minus 20 and it is minus 19.5 and minus 20.5. Yes, Ankit, noise भी कराऊंगा, noise भी कराऊंगा. Okay, so we will get this now. It will be passed through this 20 and this minus 20 only will pass, but it will be multiplied with this minus 1 upon 2j, and here we have the amplitude is 15 and this was 2, so 15 by 2 was their amplitude. Na? The sampling frequency height is 15 and the massive signal height is 1 by 2, so this is 15 by 2. So when you pass this signal through this filter, you will get only this spectrum at 20 and at minus 20. So here you will get the 15 by 2 into 1 upon 2j, and it is minus 15 by 2 into 1 upon 2j. So this will be the height. Now how do you write this? The output is, suppose y of f, which is 15 upon 2, 1 upon 2j at frequency f minus 20, and 15 by 2 height is minus 1 upon 2j and delta f plus 20. So here we can take the 15 by 2 common, and it is nothing but the this remaining term will become 1 upon 2j, and in the bracket we have delta f minus 20 minus delta f plus 20. So when you take the inverse Fourier transform, you will get 15 by 2 sine 2 into frequency is 20. So 2 into 20 pi t, which can also be written as 15 by 2 cos of 40 pi t minus 90, and the signal which we have phase which we have ignored was 45. So that 45 also you can include. So you will get minus 45. So 15 by 2 cos 40 pi t minus 45. Minus 45 means minus pi by 4. So that is how you have got this answer as 15 by 2 cos 10. It is actually not option C, option A. Guys, we are getting option A, not option C. This is 40 pi t. 40 pi t, na? This is written as 10 pi t. So 40 pi t. So answer is option A. Answer is option A, not option C. So those who have answered option C, you guys can check that where you have done the mistake. That is the major difference in these two options. Option A, 15 cos 40 pi t minus pi by 4. Now we have a bandpass sampling. So if you suppose perform the bandpass sampling, then in that case we have a sampling frequency. We can calculate it using this formula 2fc plus b divided by m plus 1 and less than 2fc minus b divided by m. Where and when you choose the sampling frequency, you have to satisfy this condition also, that the sampling frequency should be greater than 2b. Sampling frequency should be greater than 2b. So k is equal to m plus 1, k equal to fh upon b, integer part only, and m is the number of replica. If the fc is very, very greater than b, that is the narrowband signal, then the sampling frequency is twice of fh. That sine term also included, na? Sine term also included. This sine term we have written as cos. Sine term we have considered as a cos, and then we took that phase. ठीक है अंकित? So yeah, here we are talking about that if the signal is narrowband, then we will use this 2fh, or you can have one more condition, that first of all you can calculate the bandwidth if it is satisfying, if bandpass signal is not narrowband. So bandpass is fh minus fl. Then we can calculate the value of k. This is fh upon अंकित. आज आप कॉल किए थे क्या? Okay, answer this question. Okay, okay. Option A and option D. See, we have a double sideband carrier and the double sideband suppressed carrier, and this 4 gigahertz carrier is used using the low pass. So, because when you are generating the double sideband, so when you generate the double sideband, you will get this type of signal, double sideband suppressed carrier, and uh, it is 4000 megahertz. This will be 4002, and this will be 3998 in megahertz. So this is the narrowband signal. Okay, this is a narrowband signal. So narrowband signal is having the sampling frequency 2 times of highest frequency. So 2 into 4002 megahertz. That means 8.004 gigahertz. So option D will be the answer. Okay, option D will be the answer. Because this is narrowband, na? It is asking the minimum frequency of when you use the impulse train. Minimum frequency is the Nyquist rate. Nyquist rate is Fs equal to 2Fm because it is narrowband signal. And I told you that when the carrier frequency or the center frequency is very, very greater than the bandwidth, then you have to take the 2 times of highest frequency. What is the highest frequency here? The highest frequency is 4002, highest frequency, 2FH. Narrowband, because the carrier or the center frequency is 4000 megahertz and the bandwidth is 4 megahertz. So here we say that the FC is very, very greater than B, hence it is a narrowband signal, and when there is a narrowband signal, the sampling frequency is 2FH. Yes. Okay, can you answer this question? Yes, यहाँ पे gigahertz है. ये gigahertz है ना, gigahertz. There is a gigahertz only. This is megahertz, and then in the next line I have written gigahertz. ठीक है ना आशीष? Option D. here you can see that the bandwidth is 12. The bandwidth is 12 hertz. Okay, and the center frequency is 100 hertz. So here FC is not very greater. Okay, FC is not very greater than B because this is only 8 times. Very greater than means 100 times, 150, 200, 1000 times should be there. So you have to calculate the bandwidth. Bandwidth is 12 hertz. You have to calculate the value of K. K is FH upon B, which is 106 divided by 8, which give you the 8.8 something. So you will choose the value of K as 8. The third step which you will follow is will be bandwidth, sampling frequency. The sampling frequency is twice of fh upon k. So this is 2 into fh. Fh is 106 divided by k. K is 8. So it is 26.5 hertz. So this is 26.5. Answer is 26.5. Answer is 26.5. Minimum sampling frequency, because this is a band pass signal. Na? This is a band pass signal. So you have to choose the sampling frequency accordingly. We have the two different cases, whether the signal is narrow band or wide band. If it is a narrow band, then we can take the sampling frequency as twice of highest frequency. Or if it is given that you have performed the Nyquist sampling, then you can calculate the twice of highest frequency. Otherwise, the advantage of the bandpass sampling is that we can perform the undersampling, and that is when their signal is not a narrowband signal, then you can calculate the sampling frequency by following 3 steps. First step, you have to calculate the bandwidth. The second step, you can calculate the value of K. In the third step, you will calculate the sampling frequency by 2fh upon K. And the K is the integer part. Whenever you divide, the integer part will only be the K. B is 12, 96 to 106. B is the bandwidth. Bandwidth is highest frequency minus lowest frequency. The bandwidth is 12, highest frequency minus lowest frequency. Okay, leave this part. Okay, now in the quantization, we perform the quantization means we are going to sample the amplitude. We are going to discretize the amplitude. So when we perform the quantization, the continuous amplitude signal will be converted into the discrete amplitude, and we get the finite set of amplitude. So in this way, we will perform the quantization. We divide into the number of levels. The distance between the two quantization levels or the two decision boundaries are known as step size. Step size is calculated as VH minus VL divided by number of levels. कहाँ पे B equal to 8 लिखे हैं? रुको, ये B equal to 8 नहीं लिखे हैं. K, अच्छा 2fh upon K लिखा होगा ना. हाँ, तो 2fh upon K तो लिखा हूँ, ठीक तो है. टू इंटू 106 upon 8. अच्छा B इक्वल टू, हाँ यहाँ पे ये B इक्वल टू 8 नहीं है, B इक्वल टू 12 है. यस, 2fh अपॉन B, fh अपॉन fh इज 106 डिवाइडेड बाय 12. एक्चुअली इसको मैं डिवाइड कर डाला था मन में, तो ये डिवाइड कर डाला था, तो वो आंसर मैंने डायरेक्टली यहाँ लिख दिया. ठीक है, 8.8. जब डिवाइड करोगे तो आपको 8.8 मिलेगा, और जब 8.8 मिलेगा तो आपको इंटीजर पार्ट को बस चूज करना है. ठीक है, जैसे कि सपोज करो यू आर गेटिंग 7.9. so what value of K you will choose? Suppose after dividing you are getting 7.9. then what will be the value of k? What will be the value of k if you divide fh upon b and you get 7.9? Then what will be the value of k? Yes, Vikram. Floor function. So k equal to 7. K equal to 7. ठीक है आशीष, इसको आपको अप्रोक्सीमेट नहीं करना है नेक्स्ट इंटीजर में. द k is integer part means whenever you divide you have to take the floor value. After decimal whatever value will be there you don't have to take that value, only that floor value you have to take. So k equal to 7. Okay, suppose when you divide you get 6.3, then k is 6. ओके, तो मुझे बताओ कि क्वांटाइजेशन प्रोसेस में किसी को डाउट है? डू यू हैव एनी डाउट इन द क्वांटाइजेशन प्रोसेस? Do you guys have any doubt in the quantization process when we perform the quantization? What are the things we consider? Is there any doubt in this diagram? इस डायग्राम में कोई डाउट हो तो बताओ. ठीक है, so highest value minus lowest value divided by L number of quantization level. If the difference between the two quantization level and the difference between the two decision boundary both are step size, है ना, चाहे आप कोई सा भी डिफरेंस लो, both are step size, and the quantization error is the difference between the mean signal, means message signal, and quantized signal. So quantization error is the difference between the message signal and the quantized signal. And the step size is the highest value minus lowest value, that is your dynamic range, or you can also call it as a peak to peak value divided by quantization levels. Now what is the range? The range can be from minus delta by 2 to plus delta by 2. The quantization error will be maximum of delta by 2. And when we perform the encoding, yes, can you tell me what is the quantization error? What is the quantization error when we perform the uniform quantization? That is delta square by 12. Quantization error is given by delta square by 12. When we perform the encoding, the bit rate is calculated as n into fs. The number of levels are represented as 2 to the power n, where n is the number of bit per sample. N is the number of bit per sample. Signal to quantization noise ratio. The step size is VH minus VL. The quantization noise power is delta square by 12. And what is the signal to quantization noise ratio? Signal to quantization noise ratio in dB 1.76 plus 6n. This is in dB. And if you directly want to write signal to quantization noise ratio, then it is 3 by 2 into 2 to the power 2n into 2 to the power 2n. What is the Nyquist shaping criteria? So instead of taking the rectangular pulse, we take the Nyquist pulse. Nyquist pulse will be sinc function, which is going to give you the value 0 in the integer multiple of TB. So only in the integer multiple of TB we have a 0 value. 6.02. That is not necessary. 6.02 or 6n, that is okay. Guys, so we have a scholarship test also, and also mega mock test. You can appear on that. That is, you can register, and the link is given in the description. Okay, can you solve this question? 1. No. See, here we have a 1-bit quantizer, 1-bit quantizer, and we have the signal which is quantized. So this is a continuous time signal, and the PDF is given because it is present in all over this 0 to infinity. We can say that it is a continuous time signal. This x-axis is your message signal value. The message signal is having the value from 0 to infinity, and its probability distribution is given in the exponential form, and we are dividing it into the two levels. So this is our decision boundary. This is our decision boundary. Let us take this value as a threshold value as given in the question. This is our first region. This is our second region. Because it is a 1-bit quantizer, so the number of bit is 1. That means the number of quantization level is 2 to the power n, that is 2. So there are two levels, one level and the second level. So and both the levels are having the equal probability. So probability of region 1 is equal to probability of region 2, that is equal to 1 by 2. And we also know that the area under the probability density function gives probability of that region. Okay, so now the probability of region 1, if I want to calculate, then the probability of region 1 is area under this, means 0 to VTH, we have to integrate the fx of x dx. So this is equal to 1 by 2, and we have 0 to VTH. This is 2 into e to the power minus 2x dx. So it is 0.5, and this is 2 times of e to the power minus 2x divided by minus 2, limit from 0 to VTH. 2 and 2 will get cancelled, and we will get 1 minus 2 VTH. So it would be 0.5 equal to e to the power minus 2 VTH, and when we take the natural log, this is 0.693 equal to minus will become plus, so minus 0.693, so minus 2 VTH, and when we calculate the VTH, it will be 0.348 or 346 something, 346, 0.346 will come. Any doubt in this question? Any doubt in this question? Okay, now can you answer this question? In a PCM system, the signal MT is sin 100 pi t plus cos 100 pi t is sampled at the Nyquist rate. The sample are processed by the uniform quantizer with the step size of 0.75 volt. The minimum data rate of the PCM system in the bit per second is. So as you can see that we have a step size. And first of all, we can write this message signal as root 2 cos of 100 pi t minus 45 degree. Okay. Now our message signal frequency is 50 hertz. And because we are sampling in the Nyquist rate, so it is 2 times of FM. That means it is 100 hertz. Okay, the step size is delta is equal to 0.75, which is highest value minus lowest value divided by number of levels. So that is VL is equal to highest value is 2 root 2 divided by 0.75, which will be 3.77. So to represent the 3.77 level, minimum number of bit required will be 2. Okay, number of bit will be 2. So now bit rate is nothing but n into fs. So n is 2 and fs is 100. So it is 200 bits per second. So answer is 200. Yes, Ankit, correct. Answer is 200. 200 is the right answer. Okay, now can you answer this question? Let me hide myself for a few minutes because the question is hidden. The question is hidden here, and the common data question it is there are two questions related to this particular question. The first part of this question is you have to find the value of constant, and the second part of the question would be the noise power in the range of minus A to A. So I hope that you have got the questions now. Now you have to find the value of constant. So as you can see that this is a 3-level quantizer and all are having the equal probability. So the probability of region 3, okay, the probability of region 1, region 2 and region 3 are same, which is 1 by 3. And it is nothing but the area under the region 1. So 1 by 3 area is 2a into 1 by 4. So from here you will get a equal to 2 by 3. A equal to 2 by 3. Answer is B. 2 by 3. Now you want to calculate the quantization noise power in the same region. So quantization noise power in the region minus A to A is integration from minus A to A. The quantization error is given by Q, that is the quantization error, and the PDF into dx. Or in fact, I should write dq. So minus A to A, Q is square, and probability density function is 1 by 4 and here d cube. So we will get q cube divided by 3 into 1 by 4, limit from minus a to a. So you will get 2a cube divided by 3 into 4. So value of a is 2 by 3. So it is 8 upon 27 into 1 upon 6. So here it is 3 and 4. So we will get 4 upon 81. So 4 upon 81 would be the right answer. 4 by 81. Okay. So this is 1 the 3 2 the and this is 3 into 2 is 6 and value of a is 2 by 3, which we take it as 2 by 3 cube as 8 upon 27. Yes, 4 upon 81. Any doubt in this question? Because it is asking the quantization error in the minus a to a. What is the error? Error is the input minus output. What is the input? Input is q and output is 0. So you can write actually in this form also. This is the q square dx, you can write directly. Okay, q is square into px dx, because we write the, and the quantization error is x square. So the quantization error is x square. So you can write here, this is x square and dx, x square dx. Then it is x cube by 3. You can write this. Yes, if it is not uniformly distributed, then you have to write the quantization error only. The quantization error, write the quantization error. Quantization error is nothing but the input minus output. Input minus output. Okay, this is also not uniform. We are not using the formula for a uniform quantization. I am using the general formula. That is, the quantization error is input minus output. What is input? Input is x. Because input is continuous, so it is variable, and the output is midpoint of the decision boundary. What is the midpoint of these two decision boundary? Because it is asking for the calculation of the range minus a to a, the midpoint of the decision boundary is 0. But just the important thing that why we are taking the midpoint as a decision boundary, because it is given as uniform. If it is not given as uniform, then the output will be given. So we will take input minus output, that is x, and then this error I have substituted and we have got this value. Like this. This is not a uniform quantization. Can you solve this question? This is not a uniform quantization. Yes, Ashish. Come on. See, this is the question where your doubt will be clear. If it is not uniform, then how to solve it? The signal is given. The signal is ranging from 0 to 1. Our continuous time signal and continuous amplitude signal is 0 to 1. Okay, our message signal is 0 to 1. And it is given that when the input is 0 to 1, it is uniformly distributed. So it is uniformly distributed between 0 to 1. So the PDF is also given, which is 1. So this is the PDF of the message signal is given. Now it is said that our input is ranging from 0 to 0.3. The input is ranging from 0 to 0.3. Then we are getting the error as, because we want to calculate the mean square value of quantization error. So what is the input? Input we are getting as 0 to, the input we are getting as 0 to 0.3. So input is ranging from 0 to 0.3. The output is 0. So quantization error is input minus output. Input minus output. So x minus 0. So that is x. Now it is 0.3 to 1. The input minus output. The output is 0.7. Then it is x minus 0.7. Yes, this topic is equally important for the gate instrumentation also, Binu. So now when you want to calculate the mean square value of the quantization error, the formula is integration from minus infinite to infinite q square and the probability density function dx. Now the limit is from 0 to 0.3, the quantization error is x. So this is x square and the PDF is 1 dx plus 0.3 to 1, the quantization error is 0.x minus 0.7 whole square into dx. So we will get x cube by 3, limit is from 0 to 0.3, and this is x minus 0.7 cube divided by 3, limit is from 0.3 to 1. So when you solve it, you will get somewhere 0.3 cube divided by 3. So it is the 0.1. 0.333.1, 0.09, 0.009. Okay, let me solve it. One minus 0.7, 0.3 cube again. Yeah, so it is coming as 0.0393. This is your mean square value. Mean square value. But in this question, they have asked the root mean square value. So root mean square value is root over 0.0393. Which is coming as 0.198. So according to the answer we have, options we have 0.198. Now we have a delta modulation. In the delta modulation, we have a special case of DPCM. It is also called as a 1-bit quantizer or a 2-level quantizer, and it is also known as 1-bit DPCM. In the delta modulation, we sample it almost 4 to 5 times of above the Nyquist rate, 4 to 5 times. And this is the block diagram of the transmitter. There are two important things in the delta modulation. One is the slope overload error, another is the granular noise. So slope overload error, when the slope of message signal varies very fastly. When the slope of the message signal varies very fastly in compare with the slope of the staircase, then we get the slope overload error. And when the slope of the message signal is almost flat and the staircase is hunting around that flat segment of your information, then it is called a granular noise. Okay, so to avoid the slope overload error, the slope of the staircase should be greater than or equal to the slope of the message signal. So how do we get that? So as I said that the slope of the staircase is delta upon Ts. That slope of the staircase should be greater than the slope of the message signal. The slope of the message signal is Am into 2 pi Fm. So this condition has to be applied to avoid the slope overload, or we can say that the Am should be less than equal to delta into Fs upon 2 pi Fm. Delta into Fs upon 2 pi. What is the signal to quantization noise ratio in case of the delta modulation? Signal to quantization noise ratio is delta square upon 3. Signal to quantization noise ratio is delta square by 12 for the PCM, and here for delta modulation it is delta square by 3. What is the message signal to quantization noise ratio in case of delta modulation? So it is 3 upon 8 pi square Fs upon Fm whole square. This is the pre-filtered, and the post filter is 3 upon 8 pi square Fs cube upon Fm square into Fc. Now, can you solve this question? Okay, forget about this question. Yeah, can you solve this question? कौन सा स्लाइड बिनू? प्री फिल्टर पोस्ट फिल्टर वाला आशीष? ओके, इस क्वेश्चन को सॉल्व करो, दिखाता हूँ उसके बाद. A message signal is having peak to peak value and the root mean square value. So root mean square value is 0.1. So mean square value is 0.1 whole square, which is nothing but the signal power. Okay, that is the signal power. And the message signal bandwidth is 5 kilohertz. And the bit rate is 50 kbps. Okay, and we want to calculate the signal to quantization noise ratio. And signal to quantization noise ratio means we have to calculate the signal power divided by quantization noise power. Quantization noise power. So signal power is 0.1 whole square. Now we have to calculate the quantization noise power. So the quantization noise power is delta square by 12, right? But for this, what we need to calculate here is the bit rate is given, so number of bit is required. Peak to peak value is already given. So the number of bit can be calculated by RB is equal to NFS. RB is equal to NFS. So RB divided by FS. RB is 50 and Fs is 2 into 5, that is 5. So now this is VH minus VL, which is our peak to peak value whole square divided by 2 to the power 2n into 1 by 12. So peak to peak value is 2. So this is 4 upon 2 to the power 2n that means 10 into 12. So that means we can say that this is 3 into 2 to the power 10. Now our signal to quantization noise power is 1 upon 3 into 2 to the power 10. So it is 0.01 into 2 to the power 10 into 3. So that is our signal to quantization noise power. So 1024 into 0.01 into 3, that means 30.72. So 30.72 would be the right answer for this question. 30.7. Okay. Now can you answer this question? This is the question from the time division multiplexing. Time division multiplexing. Can anyone answer this question? In a certain telemetry system, 8 message signals having the bandwidth 2 kilohertz bandwidth each are time division multiplexed using the binary PCM. The error in the sampling amplitude cannot be greater than 1% of the peak amplitude. Determine the minimum transmission bandwidth required if the raised cosine pulse with the roll-off factor alpha is equal to 0.2 are used, and the sampling rate must be at least 25% above the Nyquist rate. So it is said that the quantization error in quantization amplitude, error in quantizing the amplitude. Okay, error in quantizing the amplitude. It means that it is talking about the quantization error. Okay, it is talking about a quantization error. So if it is a quantization error, then the quantization error is given by delta by 2. So this quantization error cannot be greater than 1% of peak amplitude of the message signal. The peak amplitude is 2 into AM divided by 2 into L, less than equal to 1% of AM. So this AM and AM will get cancelled, 2 and 2 will get cancelled, L should be greater than 100. So number of bit required will be 7. So minimum 7 bit will be required. So the bit rate in case of time division multiplexing is capital N into Fs. The number of message signal, the number of users are 8. The number of bit per sample is 7. The sampling frequency is, the message signal frequency is 2 kilohertz and the sampling frequency is 25% above. So it is 1.25 times of 2 into 2 kilohertz, 2 into FM. That means 2 into 2 kilohertz. So how much it is? How much it is? 56 into 4 into 1.25. 280. So it is coming as 280 kilobit per second. Now we know that the bandwidth is given by RB by 2 1 plus alpha. Okay, so RB is 280 divided by 2. Alpha is 0.2. So we will get 140 into 1.2, it is 168 kilohertz. That is the bandwidth. So 168, yes. 168 is the right answer. Now we have a next topic, which is the bandpass transmission. Guys, now we have a bandpass transmission. In the bandpass transmission, we have a three techniques, which is amplitude shift keying, frequency shift keying, and the phase shift keying. Amplitude shift keying means we perform the amplitude modulation like analog communication, but here the amplitude changes according to the binary data. Whenever the binary 1 will come, we will transmit the same carrier as it is without any change. Whenever we have a binary 0, we transmit no signal. So we either we get the signal or we don't get any signal. That is on and off situation. So that is why the another name of amplitude shift keying is on off key. Now in the ASK, in the PSK, the phase will be changed. So whenever the binary 1 will come, the phase will be 0 degree, and whenever the binary 0 will come, the phase will be 180 degree. And when we have a frequency shift keying, whenever we have a binary 1, we transmit high frequency. Whenever we have a binary 0, we will have a low frequency. So how 2 into L comes in the denominator? This is step size na. So step size is VH minus VL divided by L and into 2. So highest value of the message signal is AM. The lowest value of the message signal is minus AM divided by number of level into 1 by 2. So it is 2 AM upon 2L. Like this it came. Okay, it came in that way. Now you guys Okay, 1 by 2. 1 by 2 always come. Vikram, 1 by 2 will come definitely here. 1 by 2 will be definitely coming now. This delta by 2 is the quantization error. So that is why this 2 will come. This 2 is coming because of this denominator 2. Okay, this 2 is coming because of this denominator 2. Okay, so we were discussing the binary amplitude shift keying. So binary 1, whenever we have a binary 1, we have AC cos omega CT, and binary 0 means 0 signal, no signal is transmitted. The block diagram we can have is by generating the ASK signal. The ASK signal is BT into AC cos omega CT. This BT is 1 or 0, depending upon the binary data. If binary data is 1, then we have a 1, and when the binary data is 0, then we have got as 0. So okay, that is 1 and 0 we will have, and when the binary data 1 will come, the BT will be 1, and when the binary data 0 will come, the BT will be 0. So according to that, we will have either a AC cos omega CT or 0 signal. So this signal will be carrier signal is modulated. Okay, this carrier signal is modulated according to that BT 1 and 0, and we get the binary amplitude shift keying signal. So now in the receiver side, we will receive, although these are not important, so we will directly move into the bandwidth requirement. The bandwidth requirement for the race bandwidth requirement when you use the rectangular pulse. Okay, when you use the rectangular pulse, the bandwidth requirement will be 2 RB, and whenever there is a race cosine spectrum is given, whenever there is a race cosine spectrum is given, the RB should be replaced by RB by 2 1 plus alpha. The bandwidth will be given as 2 into in bracket RB by 2 1 plus alpha, and 2 and 2 will get cancelled, and we will get RB 1 plus alpha. Okay, so that is RB 1 plus alpha. Similarly, the same bandwidth we can use for the PSK signal also. So the PSK signal is also, the block diagrams are not important. The definition you have already understood, that for binary 1 we will transmit the 0 phase shift, and for binary 0 we have a 180-degree phase shift. The bandwidth requirement is 2 RB, and bandwidth requirement is 2 RB as that of the amplitude shift keying, and whenever there is a race cosine pulse given, just shift it the RB by 2 1 plus alpha. And suppose they ask you to calculate the baud rate, then the baud rate is nothing but a bit rate divided by log base 2m. M is the number of M array scheme. M array number of symbols. M is number of symbols. M is number of symbols. So for M-array PSK, the M-array PSK is the type of digital modulation method used for the data transmission, in which instead of 1 bit, we transmit 2 or more bits. So as I said that if there are more number of symbols, so M is having more number of symbols, then M is equal to 2 to the power n, and M is the number of levels or the combination possible for the n available bits. And in general, the bandwidth for any PSK scheme you can calculate using the rectangular pulse, that is for non-return 0, that is 2 RB upon log base 2m. Whenever it is asked for the race cosine pulse, then RB should be replaced by RB by 2 1 plus alpha. And the second is the spectral efficiency, that how efficient you can utilize the spectrum to calculate the bandwidth. We have a spectral efficiency that is equal to bit rate divided by bandwidth. Guys, so there is a course for the 2025, and you will get the link in the description. So, and you can contact in this number to get the detail of the complete course. Okay, and you can join this Telegram group for getting those PDFs and all. And if you want to connect to me, then you can also calculate the you can also consider this bandwidth. Yeah. So if you want this PDF, then you can connect through this Telegram group, and you can contact me for any queries. Like if you have any question, doubt in any question, then because you have only around 10 days left. So when you have 10 days, you can you may be having some doubt in the error, and you may have a doubt in the probability of error in the digital communication and match filter, information theory, Hamming code, etc. If you have the doubt in such type of questions, then you can send me the question in the Telegram group and you can tag me there. Then I will reply you. So that is why this Telegram group is there. Thank you for watching this session, guys. So we will meet in the next session, and we will be soon covering the formula. Okay, the formula series we will be taking the formula series in the next month, just before the 1 week. In the first week of Feb, okay, the first week of Feb, we will be considering the formula series. Okay. Yes, yes, definitely. I will be sending that. Thank you, Ashish. And actually, PDF, I will actually, I have lost that PDF of the analog communication and the random process revision. Actually, I forgot to, save that PDF, and because of the same name, the PDF is overlapped, and my old PDF got overlapped with the new one, and the new one was fresh one. There is nothing written. So that is why I was not sharing the PDF of the marathon session of the analog communication and the random variable and random process. Thank you. Okay, so thank you for watching this session. Let's meet in the upcoming session, which will be in the first week of Feb. We will be having the formula series. So whatever formula you have any doubt in those formulas, just send me in the Telegram. No? If you give me in the Telegram group, whatever doubt you have, if you already post me, then whenever I come with the new session, I will be coming prepared with those doubts, so that it can be clear. Because what I am going to tell, maybe it may be possible your doubt is still not clear. So if you will already inform me, sir, this is the topic where I am finding the doubt, I am facing the problem to solve the questions, then I will come with those type of questions in which you are facing some problem, maybe formula related, maybe approach related, maybe concept related. So if you have any specific doubt in the digital communication, then just send me in the Telegram. Then I will be able to connect with those questions in the next session. Okay. Thank you. Okay, Vikram, please share. So if you share, I will come with those questions. Yes, Ashish, no need to worry. No need to worry about this exam. You will be able to solve the questions in the exam. You have already prepared very well.